All right, welcome to the second half of the statistics and data analysis session. We now have Tom Rainforth speaking about nesting probabilistic programs.
Hey guys, so for those who don't know me, I'm Tom. I'm a postdoc in Oxford working with EYT, and as Jan said, I'm going to talk about nesting probabilistic programs. So one of the really interesting things in probabilistic programming is its ability to nest programs within one another. That is, we can take the outputs of one program or some other characterization and use that within another query. So we'll take this query and we'll put it in this other query. This is really interesting. It allows us to make models we couldn't otherwise write, but it does raise some questions from a more statistical perspective. For example, will this nesting allow us to encode models we otherwise wouldn't be able to encode? Do models still have a Bayesian interpretation? Are there going to be implications for our inference algorithms? The aim for this talk will be to answer some of these questions and provide a more formal notion of what we mean by nesting probabilistic programs. So we can actually answer the first of these questions very quickly. Nesting probabilistic programs does allow us to convey things we couldn't do without nesting. It's going to do that because it's going to allow us to convey nested expectations. What I mean by that is an expectation of a function of an expectation. So we're used to dealing with expectations all the time, usually with respect to posterior. But there is a more general class of models where we have this nested expectation behavior. We can add layers of nested expectations, so we can have an expectation of a function, of an expectation of a function, of an expectation, and so forth. And this is going to turn out to be a much richer class of models. And so by nesting probabilistic programs, we're going to exploit this richer class. So you have some examples here. One of the things it's going to allow us to do is to work with things like entropies and KL divergences of marginal distributions. So if you have the entropy of a marginal distribution, that's the expectation of the log of an expectation of the likelihood, and so you have this nested expectation behavior. So for these kind of nested expectations, you can't convey them in a normal expectation, so you can't convey them in a Bayesian model, and so you can't do them in a single probabilistic program. To give a maybe more pedagogical example, we could think about some agents reasoning about other agents. Or more precisely, you're going to have two poker players, and they're going to reason about each other. The first guy's not got very good cards, and initially says, I've not got very good cards, I should probably just fold. But the second guy is like, my cards are okay, but if he bets, he's probably got a good hand, so I'll fold. And then this first guy starts thinking a bit more. He's like, well, the other guy's thinking, and he might not be able to call me, so maybe if I bet, he'll have to fold, and maybe it's worth me betting. But then the second guy keeps thinking, he's like, well, maybe the first guy was actually bluffing, and maybe actually with my reasonable hand, I should be calling him. So you have this sort of meta-reasoning going on, where they're reasoning back and forth between each other. And in a more mathematical sense, we've got two agents, and those agents have different information, and so their simulation of each other, they're sort of running inference on each other, is creating this nesting behavior. So what aims might we have to look here? One of the first things we might want to say is, what problems are nested expectations? So we've shown that nesting probabilistic programs can allow us to do nested expectations, but when will this happen? What are going to be the statistical implications if we have nested expectations? Are they going to be just like normal expectations, or are they going to behave a bit differently? And if they do behave a bit differently, how might we construct our inference algorithms in a valid way so that we still get valid inference, ideally without having to uproot our current systems? So let's start by thinking about the first of these questions. When does a probabilistic program constitute a nested expectation instead of a normal one? So what we can do is we can think about different ways you might be able to nest programs. And I'm going to delineate these into three categories. The first category I'm going to call nested conditioning. So with nested conditioning, the high-level idea is we'll take one program and we'll run inference on that to get a marginal likelihood estimate. And then we'll use that marginal likelihood estimate to weight the program trace of another program. So we're factoring the probability of one program with a marginal likelihood estimate from another. The second thing we might do, I'll call nested inference. And in nested inference, we'll take one query, we'll convert that query to some posterior representation, and then we'll put that posterior representation into another query as a distribution. So we'll be sampling from one query in another query. The final thing we might do is we might use estimates as first-class variables. So we might run inference on one program, and that will generate a set of samples. We can form a Monte Carlo estimate of those, and that Monte Carlo estimate we could actually then use as a variable in another program. So let's look at these guys in a bit more detail. Let's first look at nested conditioning. So imagine we've got some query that I'll call outer. In this query, we're going to sample y from some distribution, and then maybe we're going to try and observe another query marginal likelihood. So I'm going to introduce some sort of weird distribution object nest. And what nest is going to do is it's going to run inference on this query inner, return a marginal likelihood estimate, and then weight the probability of this outer program according to that likelihood. So we can formalize this a bit more mathematically as follows. So with the outer query, we might say its unnormalized distribution is pi of y. And we can break pi of y down into two terms. The first term, which I'll call psi of y, is density terms just from this outer query. So if we ignore that inner query, what density terms were already there? The second guy is the marginal likelihood that we're taking from that inner query. So we're factoring the probability of the outer query using that marginal likelihood, so it forms a term in our overall unnormalized distribution. Obviously, we can't evaluate this guy exactly, and instead what we're going to have is we're going to have the psi terms, and then we're going to have a p hat, we're going to have a marginal likelihood estimate instead. So this is going to turn out to basically give us things equivalent to pseudo-marginal methods from the statistics literature. So if this guy is an unbiased estimator, then if we take the expectation under some distribution Q of this density estimate over Q, we're going to get the same expectation as the real estimate. So we'll get the real marginal likelihood out of this program if this is an unbiased estimator. So we can often call this proper weighting or pseudo-marginal methods, and that is going to give us correct inference, and it's going to still be a normal Bayesian model. It's going to be useful because it's going to allow us to do things from the inference perspective. So, for example, Marco's got a lot of great work about how you might use this kind of scheme to help your inference, but it's not going to extend the class of models we're actually encoding. Let's now move on to the nested inference case. So in nested inference, we're going to start with some inner query. So in this query, we might take in y and d. We're going to sample z from some distribution. We're going to factor the trace probability of that program with some observation. And then we're going to return this sampled variable z. So it's just a very bog standard query. What we can then do, though, is we're going to define another query. We'll call this outer. And that query is going to use this first query. So we might sample some variable y. And then I'm going to do something a bit weird. I'm going to introduce something I'll call conditional. And what condition will do is it will take this query and it will convert it to a posteriori representation. So this query is kind of an unnormalized density, and conditional will convert that to a normalized density function. And so this dist will be a new distribution object that represents the normalized density of this program. Then I can sample from this Z and maybe return some output. So this outer query is using inference on the inner query itself. Again, we can think about how we might mathematically formalize this. So now we're going to call the unnormalized density of our outer query pi yz. So y are the variables we're generating in this outer query. Z are variables we're generating from our inner query. So we have, again, this psi, y now is y and z. So we have terms in the outer program just from that query itself. And we have this pi z given y, and this is the normalized distribution of that inner query. So in other words, p z given y is the unnormalized distribution from the inner query over this normalizing constant by marginalizing out over z. That means that we can say the unnormalized distribution of the outer query is equal to psi pi over this normalizing constant. So what have we got now? We have something where we can't even evaluate the unnormalized target density. We've got this intractable integral that means we can't evaluate this guy exactly. What's just known in the statistics literature is a doubly intractable distribution. You have a parameter-dependent normalization constant that we can't evaluate. So what we're going to have to end up doing is we're going to have to approximate the posterior for this inner query. We don't have the actual posterior, we have some approximation. So we have that the joint of the outer query is approximately, again, the psi term times some approximation. Now we can look at what this might happen if we run inference. Again, we'll just use importance sampling as an example. And we see that the expectation of a Q of this target over Q is going to give us something like this. So we have the expectation under a proposal Q. We've got terms from our outer psi. We have the unnormalized target associated with the inner program, the correcting factor for the normalized something, and then this guy. And this guy is the normalization constant for the inner query given y. So it's a conditional normalization constant. So what we can think about what's happening here is we've taken a query and we've locally normalized it. We've had a query and we've sort of said this guy needs locally normalizing and then put it back in. And this has created a nested expectation, as I spoke about before. We have an expectation of a function of an expectation where that function is 1 over. So it's a particular case of these nested expectation problems. And so it's going to take us beyond the standard setting. let's move on to the estimates as variables case. So here, we're going to start with some inner query, inner Q. We're going to create a function that will make a Monte Carlo estimate for that inner query. And then we're going to make another query that uses this Monte Carlo estimate function itself. So it's going to call this inner expectation function, and it's going to make it a variable in the outer program. So we've got a Monte Carlo estimate from one program, and we're using that estimate as a variable in the other program. So this is actually an important set of equations that are Bayesian experimental design equations. And so we see that there's important problems that we need this kind of setup to be able to encode. Again, we can think about how we might mathematically formalize this. And we're now talking about an unnormalized density for our program pi of y. And this is now psi y of z given y. So if we could do that expectation exactly, the z would be a deterministic function of the y, and we'd have that other variables in the outer program. But we can't calculate this Monte Carlo, the expectation exactly. We have a Monte Carlo estimate instead. We have a z hat. And so we're approximating this density by taking a density of these two guys. Again, we can think about taking an expectation of Q, look at the marginal likelihood, and now we've got this expectation of Q of psi y expectation of z hat over Q. And this is now looking very much like nested expectations of an expectation, of a function, of an expectation. And so we see now we have a pretty generic nested expectation case. So what we've seen is that nested conditioning was still giving us the same models. It was still a standard expectation. The nested inference and these estimates of variables are cases of nested expectations. So if we care about the statistical implications, we need to look at the statistical implications of nested expectations themselves. So this takes us to some earlier work we did at ICML on nesting Monte Carlo estimators. And in here, what we're going to do is we're going to say we've got these nested expectations, and we're going to replace each with a Monte Carlo estimator. So for our outer query, we have the Monte Carlo estimate I0. And that's empirical sum of some samples, but where one of these samples is itself a Monte Carlo estimate. So this is a Monte Carlo estimate for the inner query. And so in the, say, the nested inference case, this is a Monte Carlo estimate of the marginal likelihood. And so we have for each y in our outer estimator, we have a separate Monte Carlo estimator for our inner query. So we can look at this a bit pictorially. We can say is y's in blue at the top. Each of those is a new sample for the outer query. Each time we sample a new sample from the outer query, we're going to generate these N1 samples from the inner query, such that this red box is associated with one call of the outer query. We then have multiple calls of the outer query giving us this green box as the total set of samples we've got. So we have these N0 samples of the outer query and N1 samples of the inner query for each of those samples. So the cost here is going to be proportional to the volume of this box. So if you had extra layers of nesting, it would also come out the page and so forth, and the volume of the box is our cost. What we're going to find is that we don't just need that volume to go to infinity. We need all of the dimensions to go to infinity for convergence. Or more formally, we can say if all of our fk is continuously differentiable, then the convergence rate is as follows. So the convergence rate is order 1 over n0, 1 over the number of samples of the outermost query, plus the sum over 1 of the number of samples at each nested query. So each layer of the nested query has nk samples each time it's called, and we have the sum of those squared. So this is a variance, and so we see that the variance only depends on the number of samples in the outermost query, while the bias only depends on the number of samples in the inner queries. Critically, we see that each of these nk needs to go to infinity. So each time we call any query, we need to drive increasing number of samples for that call if we want the thing to converge overall. The other thing we can see here is we can think about the asymptotic optimizing this error in terms of the setup. So depending on how we allocate our budget between the levers, we're going to get different convergence rates. And the best convergence rate is that at each nested query, we use the square root of the number of samples in the outermost query. So there's a quirk here that's not self-similar. If we keep nesting, it's all square root of the outermost, not the parent. But this will give us the best rate. It's going to turn out this will give us a convergence rate that's order 1 over t to the 2 over 2 plus d. So t here is total cost. It's the product of all the n's. D is the number of layers of nesting. So if there's no nesting, we get Monte Carlo. We get mean squared error rate of 1 over t. With d equals 1, we get a rate of 1 over t to the 2 over 3. If d is 2, we get 1 over square root t. So it's exponentially decreasing, and things are getting harder. So we want to avoid these things if we can. But linking back, if you remember, there are problems we can't encode without these. So we can't really avoid this sometimes. They're just very expensive to actually solve. Now to talk about one of the implementation issues, though, that we have. Imagine we've already got an estimate, and now we want to update that estimate. That's kind of annoying, because we can't just draw more samples and make this wider, because that won't reduce the bias. The bias was how deep this was. So we find if we want to make our estimate better, we don't just have to draw more samples, we have to go back and refine all of our previous samples. And that's a big implementational problem. That means we have to store everything, we have to have communication. If there's lots of layers of nesting, it's going to become a complete mess. So we can have a simplification of this that's going to make things a lot easier. And that's that as we draw more samples from inner queries, we use more samples. So we might draw one sample the first time, 2, 3, 3, 4. So as we draw more as we call the inner query more often, we're going to use more samples, probably at the square root of the number of the outermost to get the best convergence rate. And it's going to turn out that doing this is actually surprisingly good in terms of performance. In fact, it's going to be provably better variance than the standard nested Monte Carlo estimate, while it's going to have a bias within a factor of 2. So we see that this much, much simpler thing where we need no communication between things, we just have to know how many times have I been called before, so how many samples should I use. This guy is going to give pretty much the same convergence rate. And we see this coming out empirically as well. So a few things going on here. So x-axis is the total number of samples. The y-axis is the mean squared error. Red is if we use a fixed number of samples in our inner query. So we see that we have this bias. We can't get below this line if we don't increase the number of samples in the inner query. We see in blue and in green the online and non-online estimators, and we see that we've got an almost exact match in practical performance. Okay, what are the take-homes then from this? So we've shown that nesting probabilistic programs allows us to encode models we couldn't encode otherwise. It's opening us up to encoding nested expectations. So in particular, the nested inference case is going to allow us to do doubly intractable problems, and this estimates as variables is going to open that further to the full set of nested expectations. We've shown, though, that we do need to be careful about how we design our inference engines. We have this particular pitfall of using an increasing number of samples at each layer of the estimator, otherwise things won't converge. We've also shown that if we just increase samples at more we call a query, that's actually going to give performance almost completely matching the performance of doing things in a non-online manner, and that's going to make everything much easier to implement. Thank you very much for listening. I'd like to thank my co-authors from the ICML paper, Rob, Hunsuk, Andrew, and Frank, who contribute a lot to the work, and hopefully there's a time for a few questions if...
Are there no questions? So I have questions, but they're all mean. So, I suggest that maybe somebody comes up with, an easy question for them. So we talked about this theory of mind, right?
Yeah.
So would you say that theory of mind is a nested expectation problem, a doubly intractable distribution, or actually none of the above?
Good question. So Noah's done a lot of great work on this in the past, and so it ends up being quite subtle. So in the poker example, each of these guys had different information. So you can think about sort of the classic shelling coordination game. So there's two people, and one is wondering whether to go to the pub or to the coffee shop, and they think about what the other guy wants, and as they think behind it, they sort of settle on a decision. But that problem actually turns out not to be nested, because in that problem, they have the same information, and so you can collapse it to one model. So it's actually a subtle question about exactly how you model it. So I would say in general, it probably is, because when you're reasoning about the decisions of someone else who has different information, but yeah, I'll trail off.
I thought that was a great answer. All right, let's thank the speaker again.